Welcome back to Scientific Discovery Hub, where we unlock the universe's greatest mysteries. Have you ever wondered what cosmic secrets lie hidden in the icy hearts of comets? Or what happens when a visitor from another star system slips silently through our solar system? Well, hold on to your telescopes. 2025 is set to deliver two astronomical spectacles that will blow your mind. See 2025 R2 SWAN, a dazzling comet that might light up Earth's skies with a meteor shower, and 3i Atlas, an enigmatic interstellar wanderer on a one-way trip out of our cosmic neighborhood. In this video, we'll take you on a journey through time and space to uncover what these celestial oddities reveal about the birth of stars, the chemistry of alien worlds, and our place in the universe. First, we'll explore why comets are like time capsules from the dawn of the cosmos. These icy relics, forged in the cold dark of space, carry clues about the early universe, and 2025's comets are special. While C2025 R2 could explode into a fiery demise, scattering dust that becomes a meteor shower, 3i Atlas is making headlines as the third known interstellar object to visit our solar system. But what makes this one different? We'll dive into its bizarre chemistry. Think carbon dioxide, cyanide, and more, and how its origin story might rewrite our understanding of planetary formation. You'll learn why 3i Atlas's silent exit is just as fascinating as its arrival. Is it a relic from the Milky Way's ancient past? Could its composition hint at life's building blocks in other star systems? We'll also compare its fate to C2025 R2's dramatic disintegration, showing how both events highlight the delicate balance between creation and destruction in the cosmos. Plus, we'll peek into the future of comet hunting, revealing how cutting-edge telescopes and citizen scientists are revolutionizing our quest to track these cosmic travelers. By the end of this video, you'll see comets not just as fleeting streaks of light, but as storytellers of the universe, bridging the gap between Earth and the stars. So whether you're a seasoned stargazer or a curious newcomer, this is one cosmic adventure you won't want to miss. Hit play to dive deeper. And don't forget to like, subscribe, and hit that notification bell for more mind-bending science. The universe is full of wonders. Let's explore them together. In the vast uncharted expanse of the cosmos, comets drift like ancient scrolls, inscribed with the secrets of starlight and time. These icy wanderers, born in the frigid outskirts of planetary systems, are more than transient glimmers in the night sky. They are emissaries from the universe's forgotten epochs, bearing evidence of its earliest days and its farthest reaches. In the year 2025, two extraordinary comets, C2025 R2 SWAN and 3i Atlas, will grace our celestial neighborhood, each with a story to tell. While one may disintegrate into a cascade of dust and fire, the other will vanish into the void, carrying with it the chemical fingerprints of a star system long since vanished. Together, they remind us that the universe is not silent. It speaks in the language of comets, and those who listen may glimpse the grand tapestry of existence itself. The concept of comets as cosmic messengers is as old as human curiosity. Ancient civilizations interpreted their sudden appearances as omens, their ghostly tales weaving tales of gods and chaos. Yet modern science reveals a deeper truth. Comets are time machines. Their nuclei, composed of frozen gases and primordial dust, preserve material from the nebula that birthed our solar system 4.6 billion years ago. When sunlight warms a comet's fragile heart, it sheds its secrets in a luminous shroud of gas and debris, a fleeting act of cosmic communication. In 2025, as C2025 R2 SWAN and 3i Atlas traverse their respective paths, we stand at the threshold of a dialogue between humanity and the infinite. What will these comets reveal? How will their journeys reshape our understanding of the cosmos? The answers lie in the heavens, waiting to be deciphered. Comets are the product of a cold, distant past, formed in the outermost regions of planetary systems, the Oort cloud for our own solar system. These icy bodies consist of a mixture of water ice, methane, ammonia, carbon dioxide, and silicate dust. For millennia, they slumber in the dark, their orbits perturbed only occasionally by gravitational tugs from passing stars or giant planets. When a comet ventures inward toward a star, solar radiation ignites its frozen core, transforming volatile compounds into gas and propelling dust into the void. This process creates the comet's coma, a glowing halo of ionized gas, and its tail, a stream of particles that stretches millions of kilometers. Each comet's journey is unique, dictated by its orbital path and the forces that govern it. C2025R2, SWAN, exemplifies the fragility of these cosmic travelers. Discovered in September 2025 by Vladimir Bezugli, using the SWAN instrument aboard the Solar and Heliospheric Observatory, SOHO. This comet reached perihelion, its closest approach to the Sun, on 12 September 2025 at a mere 0.5 AU, 75 million kilometers. Its rapid brightening from magnitude 11 to 6.2 in just over a month hinted at an impending transformation. By October 2025, as it neared its closest approach to Earth at 0.26 AU, 39 million kilometers, observers speculated whether it would survive its encounter with the Sun or disintegrate into a meteor-producing storm. Such outcomes are not uncommon. Many comets, unable to withstand the intense heat and tidal forces near the Sun, fragment into clouds of dust and gas. If C2025R2 meets this fate, its remnants could ignite a meteor shower in October 2025, a celestial fireworks display born from the ashes of a dying comet. Meanwhile, 3I Atlas represents a rarer phenomenon, an interstellar comet. Unlike C2025R2, which hails from the depths of our solar system, 3I Atlas originated from another star system, traveling at a blistering 58 kilometers per second, 36 ms, as it crossed the boundary of our cosmic neighborhood. Discovered on 1 July 2025 by the Atlas Survey Telescope in Chile, this comet followed a hyperbolic trajectory, a path so elongated that it would never return to the Sun. Its nucleus, shrouded in a coma rich in carbon dioxide and water ice, offered scientists a glimpse into the chemistry of a distant world. Observations by the James Webb Space Telescope revealed traces of cyanide and nickel, elements that hinted at a violent past or a unique environment in its home system. As 3I Atlas approached perihelion on 29 October 2025, its journey underscored a profound truth. The universe is a web of interconnected worlds, and comets are the threads that bind them. The science of comets extends beyond their individual stories. By studying their composition and behavior, astronomers reconstruct the conditions of the early solar system and beyond. For instance, the isotopic ratios in cometary ice can reveal whether a comet formed in a region with different temperatures or chemical abundances than ours. Similarly, the trajectories of interstellar comets like 3I Atlas provide clues about the dynamics of star systems and the frequency of interstellar encounters. In 2025, as these two comets illuminated the skies, they served as laboratories for testing theories about planetary formation, stellar evolution, and the distribution of matter in the galaxy. Yet the study of comets is not purely academic. Their interactions with planets and moons can shape the habitability of worlds. For example, comets may have delivered water and organic molecules to early Earth, seeding the conditions necessary for life. The potential for such cosmic delivery remains a tantalizing mystery, one that 3I Atlas and C2025R2 could help unravel, whether through direct impact or the release of volatiles into planetary atmospheres. Comets play a role in the cosmic cycle of creation and destruction. The disintegration of C2025R2, SWAN, and the interstellar origin of 3I Atlas invite profound questions about the nature of the universe and our place within it. If C2025R2 dissolves into a meteor storm, its legacy will endure in the form of stardust raining through Earth's atmosphere. Each grain of comet-derived dust carries a chronicle of its journey from the Oort cloud to the Sun, preserving isotopic signatures and mineralogical clues that could inform studies of the solar system's formation. Meteor showers, often dismissed as fleeting spectacles, are in fact moments of cosmic intimacy, brief collisions between Earth and the remnants of ancient comets. By analyzing the chemical composition of these particles, scientists may uncover new insights into the distribution of materials in the early solar system and the processes that shaped it. For 3I Atlas, the implications are even more staggering. As the third confirmed interstellar object to visit our solar system, it challenges assumptions about the rarity of such visitors. The fact that 3I Atlas originated from the thick disk of the Milky Way, a region populated by some of the galaxy's oldest stars, suggests that interstellar comets may be more common than previously thought. If comets like 3I Atlas are frequent travelers between star systems, they could serve as vectors for the exchange of materials and potentially even life. The presence of complex organic molecules in 3I Atlas's coma raises the possibility that interstellar comets might carry the building blocks of biology across the cosmos. Could a seed of life, dormant in a comet's icy heart, one day germinate on a distant planet? The idea, once the realm of science fiction, now finds support in the real-world chemistry of comets. Moreover, the study of 3I Atlas offers a rare opportunity to compare the architecture of alien star systems with our own. By analyzing its orbital parameters and composition, astronomers can infer the conditions of its home system. For example, the high concentration of carbon dioxide in 3I Atlas's coma contrasts with the water-dominant ice of many solar system comets, suggesting differences in the chemical environments of its origin. Such comparisons may one day reveal patterns in the distribution of planetary systems across the galaxy, helping to answer the question, are we alone in the universe? The exploration of comets also intersects with the search for habitable exoplanets. The delivery of water and organics via comets could influence the emergence of life on distant worlds. If comets like 3I Atlas are common, they might act as cosmic couriers, ferrying essential ingredients for life to planets in diverse star systems. This perspective reframes comets not as isolated phenomena, but as integral players in the grand narrative of cosmic evolution. As we trace the journeys of C2025 R2 SWAN and 3I Atlas, we begin to see the universe not as a static expanse but as a dynamic, ever-changing tapestry. Comets, in their brief moments of brilliance, remind us that the cosmos is alive with motion and transformation. Yet their stories do not end with their disintegration or departure. The dust of C2025 R2 may one day rain down on Earth, while the memory of 3I Atlas's passage lingers in the data of telescopes and the imaginations of those who watched its silent flight. These events are not mere endpoints. They are invitations to ponder the interconnectedness of all things. In the next segment, we will delve into the final chapters of these comets' journeys, how C2025 R2's disintegration could illuminate the skies with a meteor storm, and how 3I Atlas's escape from the solar system might offer clues about the future of interstellar travel. By examining their fates, we uncover not only the mechanics of comets, but also the enduring wonder of a universe that constantly surprises us. The cosmos speaks in many voices, and in 2025, we are privileged to hear two of its most haunting and beautiful. This script expands the original segment into a contemplative, scientifically grounded narrative, adhering to the required structure and emphasizing cosmic wonder. Each section weaves together observational data, theoretical insights, and philosophical reflections, creating a cohesive and immersive exploration of comets as cosmic messengers. In the vast silent expanse of the cosmos, comets emerge as fleeting spectacles, fragile, ancient wanderers that trace arcs of ice and dust across the heavens. They are cosmic storytellers, bearing whispers of the universe's earliest days, their glowing tails etched against the blackness like brushstrokes in an eternal mural. Among the countless celestial bodies that populate our night skies, comets hold a special place. They are relics of the solar system's formation, born in the frigid outer reaches and occasionally nudged inward by gravitational tugs of distant planets. Yet their lives are precarious, marked by cycles of birth, brilliance, and often violent demise. The year 2025 witnessed three extraordinary comets, each offering a glimpse into the dynamic interplay of forces that govern the cosmos. C2025 F2 SWAN, a sun-grazing comet discovered by the Solar and Heliospheric Observatory (SOHO), spiraled toward its fiery end, its nucleus disintegrating under the sun's relentless heat. 3I Atlas, an interstellar traveler hailing from the depths of the Milky Way, traversed our solar system on a hyperbolic path, its origins steeped in mystery, and its chemical composition hinting at alien worlds. And C2025 R2 SWAN, another sun skimmer, danced across the skies before vanishing in a burst of stardust, its legacy destined to become a meteor shower. Together, these comets paint a picture of impermanence and transformation, reminding us that even the most ephemeral phenomena are woven into the grand design of the universe. To understand the fates of these comets is to grapple with the delicate balance between creation and destruction. Their journeys from the icy vaults of the Oort cloud to the scorching embrace of the sun, or from distant star systems to our own, are testaments to the ceaseless motion of matter and energy in the cosmos. They challenge us to peer beyond the immediate, to see not just the glittering spectacle of a comet's passage, but the deeper truths hidden within their trails of ice and gas. Comets are not immune to entropy. Their nuclei, composed of volatile ices and porous rock, are held together by a tenuous equilibrium of gravity and cohesion. When a comet ventures too close to the sun, this balance is disrupted. The solar radiation bombards the nucleus, heating its surface and triggering sublimation, the direct transformation of ice into gas, as water, carbon dioxide, and other volatiles escape into space. Jets of material erupt, eroding the nucleus and building the luminous coma and tail that define a comet's appearance. Yet this process is not always gentle. For comets like C2025R2 SWAN, the sun's fury becomes a harbinger of their end. Discovered in September 2025 by amateur astronomer Vladimir Bezugli through SOHO's SWAN instrument, C2025R2 was initially a quiet presence in the constellation Virgo, its tail stretching 2 degrees across the sky. But as it neared perihelion, the closest point in its orbit to the sun, its behavior grew erratic. By early October, the comet had brightened to magnitude 6.9, visible in binoculars from the southern hemisphere. Yet this brilliance was deceptive. The nucleus, already weakened by prior outbursts, could not withstand the escalating thermal stresses. On 22 April 2025, it shattered, releasing a cloud of dust and fragments that would one day return to Earth as meteors. The disintegration of C2025R2 followed a pattern observed in many sun-grazing comets: a rapid increase in brightness, followed by a sudden fade, the nucleus perhaps no larger than a kilometer in diameter, fractured under the strain of differential heating. Surface layers, already pitted by prior eruptions, sloughed off, exposing deeper strata of ice and rock. The resulting dust cloud, glowing faintly in reflected sunlight, trailed behind the comet's path, a ghostly echo of its former self. Yet this is not an end but a metamorphosis. The particles released by C2025R2 will orbit the sun for centuries, gradually drifting into new trajectories. When Earth intersects this debris trail in October 2025, the grains will collide with our atmosphere at hypersonic speeds, compressing air and generating incandescent streaks, meteors. These brief flashes of light will carry the chemical signature of their parent body, allowing scientists to analyze the composition of a comet that no longer exists. In this way, the death of C2025R2 becomes a gift to future generations, a bridge between the ephemeral and the eternal. The disintegration of comets is a reminder of the universe's indifference to permanence. Yet, in their demise, comets offer insights into the fundamental processes that shape planetary systems. The study of C2025R2's meteor shower, for instance, could reveal the distribution of volatile materials within its nucleus. Were the gases uniformly mixed, or did pockets of carbon dioxide or methane dominate? Did the nucleus contain organic compounds, hinting at the ingredients for life? Each meteor is a data point, a fragment of a story written in the language of chemistry and physics. Moreover, the fate of C2025R2 underscores the fragility of celestial bodies. Unlike asteroids, which are held together by stronger gravitational forces, comets are held in place by weak molecular bonds and the pressure of internal volatiles. Their survival depends on their distance from the sun and the stability of their orbits. Ampere's single outburst, like the one observed in April 2025, can tip the scales from resilience to collapse. This vulnerability makes comets invaluable probes of solar activity and orbital dynamics. By studying their disintegration, scientists can refine models of solar wind interactions, tidal forces, and the structural integrity of icy bodies. The broader implications extend beyond individual comets. The debris trails left by disintegrating comets contribute to the interplanetary dust environment, a diffuse reservoir of material that influences everything from planetary atmospheres to the formation of new stars. Some of this dust may eventually settle on planets, delivering primordial compounds to their surfaces. In this sense, the death of a comet is not merely an endpoint, but a continuation of cosmic recycling, a thread in the tapestry of matter that connects the smallest particles to the largest structures in the universe. Philosophically, the transient nature of comets mirrors the human condition. Their brief moments of brilliance, followed by inevitable decay, invite reflection on the impermanence of existence, yet their legacies persist, not as static monuments, but as dynamic processes. The meteor shower from C2025 R2 will not be a singular event, but a recurring phenomenon, a testament to the cyclical rhythms of the cosmos. Each meteor, a fleeting spark, carries the memory of a comet that once danced in the dark, while C2025 R2 faded into stardust. Another comet, 3I Atlas, was making headlines for a different reason. Unlike the sun-skimming comets of our solar system, 3I Atlas was not bound by the sun's gravity. Instead, it followed a hyperbolic trajectory, hurtling through the inner solar system at a velocity of 58 kilometers per second. This speed, far exceeding the escape velocity of the solar system, marked 3I Atlas as an interstellar traveler, a rare visitor from the depths of the Milky Way. Its discovery in July 2025 by the Atlas Survey in Chile opened a window into the enigmatic realm of interstellar objects, a class of celestial bodies that challenge our understanding of planetary formation and galactic dynamics. To comprehend the significance of 3I Atlas, we must first unravel the language of its motion. The comet's orbital eccentricity, an indicator of the shape of its path, exceeded 6, a value so extreme that its trajectory appeared almost straight line rather than curved. This hyperbolic path meant that 3I Atlas would not return to our solar system. It had arrived from interstellar space and would soon depart, carrying with it clues about its distant home. The question that loomed over astronomers was simple yet profound. Where had it come from? The answer lay in the comet's velocity vector. By breaking down its hyperbolic excess velocity into components, scientists determined that 3I Atlas originated from the direction of the galactic center, deep within the spiral arm of the Milky Way. More intriguingly, its vertical velocity relative to the galactic plane suggested it hailed from the thick disk, a population of ancient stars with lower metallicity than the Sun. This implied that 3I Atlas could be billions of years old, predating our solar system by eons. If confirmed, it would be the oldest known comet, a relic from a time when the Milky Way itself was young and forming. The journey of 3I Atlas is not merely a tale of cosmic travel, but a puzzle waiting to be solved. Its chemical composition, analyzed by telescopes like Hubble and James Webb, revealed a curious mix of carbon dioxide, water ice, and nickel vapor. These findings raise questions about the conditions of its home system. Was it a cold, distant world, where CO2 dominated over water ice? Or had it undergone a different evolutionary path, shaped by the unique environment of its native star? The answers could reshape our understanding of how comets form in other star systems, and what they carry with them into the void. As 3I Atlas continues its outbound journey, its path will take it past Mars, Venus, and Jupiter, offering opportunities for further observations. While it remains faint from Earth, its brightness from the Martian surface may allow orbiters to study it up close. These data will be critical in piecing together the comet's history and the broader context of interstellar comets. In the coming months, as 3I Atlas disappears from view, it will leave behind a trail of questions and a promise that the universe is far stranger and more interconnected than we dare imagine. The stories of C2025 F2, 3I Atlas, and C2025 R2 are threads in the vast, intricate tapestry of the cosmos. They remind us that the universe is not a static realm, but a dynamic, ever-changing theater of creation and destruction. Comets, in particular, embody this duality. They are born in the cold crucibles of protoplanetary disks, live as transient beacons in the night sky, and die in fiery bursts of light, or, as in the case of C2025 R2, in a slow, graceful unraveling that sows the seeds of future phenomena. Interstellar comets like 3I Atlas add another layer to this narrative, bridging the gap between solar systems and galaxies. They are messengers from the unknown, carrying with them the fingerprints of alien worlds and the echoes of cosmic history. Their discovery is a humbling reminder of humanity's place in the universe. We are but observers on a tiny blue dot, peering into an ocean of stars, seeking meaning in the patterns of light and shadow. As the year 2025 draws to a close, The legacies of these comets will endure. The meteor shower from C2025R2 will streak across Earth's skies, a fleeting reminder of a comet's final act. The data from 3I Atlas will fuel decades of research, challenging and refining our theories of planetary formation and interstellar travel. And the comets themselves, whether scattered into dust or hurled into the galactic abyss, will remain part of the cosmic dance, a testament to the beauty of impermanence in a universe that thrives on change. In the end, the study of comets is not just an exercise in astronomy, it is a meditation on the nature of existence. They teach us that endings are beginnings, that destruction is the price of evolution, and that even in the vast, indifferent cosmos, every particle has a story to tell. As we gaze upward, we do not merely watch the heavens, we listen to the whispers of the universe, carried on the tales of passing comets. In the vast, silent expanse of the universe, where stars burn like ancient sentinels and galaxies spiral in eternal waltzes, comets emerge as transient whispers from the void. These icy wanderers, born in the cold outer reaches of star systems, are time capsules of cosmic history. They carry secrets of the solar system's infancy, relics of interstellar journeys, and glimpses into the chaos of stellar nurseries. Among the countless comets that have graced human skies, a few stand apart, not merely as celestial phenomena, but as enigmatic messengers from the furthest corners of space. In the year 2025, the heavens unveiled three extraordinary comets: C2025F2 SWAN, 3I Atlas, and C2025R2 SWAN. Each tells a story of perilous journeys, fragile existence, and the raw, untamed forces of the cosmos. C2025F2, a disintegrating comet that once promised brilliance, reminds us of the fragility of celestial bodies. 3I Atlas, an interstellar traveler, challenges our understanding of the universe's boundaries. And C2025R2, with its potential to seed Earth with a meteor shower, bridges the ephemeral and the eternal. Together, they invite us to ponder our place in the universe, a fleeting moment in a tapestry woven over billions of years. This script is a contemplative journey through these comets, exploring their origins, their fates, and the profound questions they ignite. Let us begin with C2025F2 SWAN, a comet whose brief, brilliant dance across the sky ended in disintegration, leaving behind only a cloud of dust and unanswered questions. C2025F2 SWAN was first glimpsed in the Lyman R light captured by the Solar and Heliospheric Observatories SWAN instrument on 22 March 2025. Discovered independently by Vladimir Bezugli, Michael Matiasso, and Rob Matson on 29-31 March. The comet initially shone at magnitude 11, its faint glow betraying a distant and delicate presence. At the time of discovery, it was 1.62 astronomical units (AU) from Earth and 0.92 AU from the Sun, its solar elongation of 28 degrees placing it in the twilight sky for observers in the Northern Hemisphere. The comet's trajectory was a testament to the gravitational tides that shaped the solar system. With a nearly parabolic orbit, C2025F2 was on a one-way journey from the outer solar system, having spent millennia drifting inward from a distance of 3,750 AU, over 561 billion kilometers from the Sun. Calculations based on its orbital parameters suggested a barocentric orbital period of roughly 80,000 years, meaning the comet had traveled for 40,000 years to reach the inner solar system. Its perihelion closest approach to the Sun was set for 12 September 2025, at a scorching 0.333 AU 49.8 million kilometers, skimming the inner edge of Mercury's orbit. In the weeks following its discovery, C2025F2 brightened as its icy nucleus warmed under the Sun's relentless heat. By early April, it had reached magnitude 10.6, its coma, a cloud of gas and dust surrounding the nucleus, expanding to 2 arc-minutes in diameter. Observers like Michael Jaeger and Kelvin Yoshimoto captured its fleeting tail, which stretched up to 35 arc-minutes in length, a shimmering thread of vaporized ice and debris. On 4 April, Mike Meyer described the comet as resembling a well-concentrated globular cluster, its faint glow a haunting reminder of its fragility. Yet the comet's fate was sealed. In mid-April, as it neared perihelion, C2025 F2 began to disintegrate. AMPA's violent outburst on 5 April briefly boosted its brightness to magnitude 8.6, but this was followed by a rapid fading. By 22 April, the nucleus had vanished entirely, leaving behind only a diffuse dust cloud. The disintegration likely began during the outburst, as internal stresses from solar heating fractured the nucleus. Though fragments temporarily brightened the comet to magnitude 9.3, they soon dissipated into the void. C2025 F2's journey mirrors the paradox of comets. Born in the cold depths of space, they flourish in the sun's embrace only to perish in its glare. Its disintegration underscores the precarious balance between creation and destruction in the cosmos, a theme echoed in the stories of 3I Atlas and C2025 R2. C2025 F2's disintegration is not an isolated event. Comets are inherently unstable, their survival dependent on the volatile materials that sustain them. When a comet's nucleus, composed of ice, rock, and organic compounds, ventures too close to the sun, its surface sublimates, transitioning directly from solid to gas, releasing dust and gas that form the coma and tail. This process, while beautiful, is also self-destructive. The repeated cycles of heating and cooling erode the nucleus, eventually fracturing it into smaller pieces or reducing it to a barren core. For C2025 F2, the final phase of its life was marked by a dramatic outburst on 5 April. Such events are often triggered by the sudden release of trapped gases beneath the nucleus's surface. As volatile ices warm and expand, they build pressure until the crust ruptures, sending plumes of material into space. In C2025 F2's case, this explosion briefly reversed its fading trend, but it also accelerated its demise. The nucleus, weakened by fractures, could not withstand the sun's tidal forces or the thermal stress of its final approach. The comet's fate raises questions about the frequency of such disintegrations among long-period comets. Many of these objects originate in the Oort cloud, a spherical shell of icy bodies extending up to 100,000 AU from the sun. Perturbations from passing stars or galactic tides occasionally nudge these comets toward the inner solar system, where their survival is uncertain. Studies suggest that a significant fraction of comets disintegrate before reaching perihelion, their journeys ending in silence. C2025 F2 is a poignant example of this cosmic lottery, a traveler that dared to venture close to the sun, only to be consumed by its own brilliance. Yet even in death, C2025 F2 left its mark. The dust cloud it shed drifted outward, a transient echo of its existence. Some particles may one day collide with planets or moons, delivering primordial material to new worlds. Others will continue their lonely voyage, scattered by solar winds and the gravitational pull of planets. In this way, the comet becomes part of the cosmic cycle, its remnants repurposed by the universe. While C2025 F2's story is rooted in the solar system, another comet, 3I Atlas, defies such confines. Discovered by the Asteroid Terrestrial Impact Last Alert System, Atlas, on 1 July 2025, 3I Atlas is an interstellar traveler, a visitor from a distant star system. Its hyperbolic trajectory, a path unbound by the sun's gravity, proves its extraterrestrial origin. With a velocity of 58 kilometers per second, 36 ms, relative to the sun, 3I Atlas moves faster than any natural body within our solar system, hurtling through space at a speed that ensures its escape. 3I Atlas's arrival challenges our understanding of the universe's interconnectedness. Until 2017, when the interstellar asteroid 1I Oumuamua was discovered, scientists believed such objects were rare. But 3I Atlas, the third confirmed interstellar visitor, suggests that the cosmos is a bustling highway of rogue bodies, many of which originate from the chaotic disks of young star systems. What makes 3I Atlas particularly intriguing is its origin. Tracing its trajectory backward, astronomers determined that it hailed from the direction of the Milky Way's thick disk, a region populated by ancient stars, some of which are over 10 billion years old. If 3I Atlas indeed originated from this population, it may be older than the solar system itself, a relic from an era when the galaxy was young and star formation was rampant. 3I Atlas's discovery on 1 July 2025 marked a pivotal moment in astronomy. Initially mistaken for a faint asteroid, the object's trajectory quickly revealed its interstellar origins. With an orbital eccentricity of 6.141, far exceeding the 1.0 threshold for hyperbolic orbits, it was clear that 3I Atlas was not gravitationally bound to the Sun. Its velocity, measured at 58 kilometers per second, further confirmed this, as it exceeded the solar system's escape velocity at that distance. The comet's path was meticulously mapped using data from the Hubble Space Telescope, the James Webb Space Telescope, JWST, and ground-based observatories like the Very Large Telescope. These observations revealed that 3I Atlas approached the Sun from the direction of the constellation Sagittarius, near the Milky Way's galactic center. Its trajectory, retrograde and inclined 5° relative to the ecliptic, meant it moved in the opposite direction to most solar system bodies, a stark reminder of its alien heritage. 3I Atlas's closest approach to the Sun occurred on 29 October 2025, at a distance of 1.36 AU 23 million kilometers, between Earth and Mars. Despite this relatively modest perihelion, the comet's velocity ensured it would escape the solar system entirely, carrying with it fragments of its home star system. The comet's nucleus, estimated to be less than 1 kilometer in diameter, was obscured by a coma rich in carbon dioxide, water ice, and organic molecules. Spectroscopic analysis by JWST revealed a composition unlike any native comet, with elevated levels of carbon monoxide and carbonyl sulfide. These findings hinted at a formation environment colder and drier than the Kuiper Belt, suggesting 3I Atlas originated in a distant frigid region of its host system. Perhaps most astonishing was the detection of nickel vapor and cyanide gas in the coma. These elements, typically associated with high-temperature processes, suggested that 3I Atlas had experienced periods of intense heating, possibly from a close encounter with its parent star or a collision with another body. Such events could have stripped away its outer layers, exposing volatile ices buried deep within. 3I Atlas is more than a passing interstellar object. It is a Rosetta Stone for understanding the diversity of planetary systems beyond our own. The comet's chemical fingerprint, rich in carbon dioxide, carbon monoxide, and complex organics, offers clues about the conditions in its home star system. Unlike comets in the solar system, which formed in the colder outer regions, 3I Atlas's high concentration of carbon dioxide implies a formation zone farther from its star than the equivalent of the Kuiper Belt. This suggests that its parent system may have harbored a more expansive reservoir of volatile materials, or that its journey involved a tumultuous history of gravitational interactions. The presence of nickel vapor and cyanide also raises intriguing questions. These elements are rare in native comets, which typically contain trace amounts of refractory materials. Their abundance in 3I Atlas could indicate a formation environment rich in metals, or a history of collisions that exposed its interior. Alternatively, the comet may have originated in a binary star system, where tidal forces could generate the heat needed to vaporize refractory elements. 3I Atlas's retrograde orbit further complicates its origin story. Retrograde motion is uncommon in the solar system, as most bodies share the prograde rotation of the protoplanetary disk. However, in binary or multi-star systems, gravitational perturbations can easily flip orbital orientations. If 3I Atlas originated in such a system, its journey may have begun with a violent ejection triggered by a close encounter with a sibling star or giant planet. The comet's age is another enigma. Based on its trajectory and the kinematics of the thick disk, estimates suggest it is between 3 and 14 billion years old, far older than the solar system's 4.6 billion years. If accurate, 3I Atlas is a relic from the galaxy's early days, predating the formation of our own star. Such an ancient object could hold chemical signatures from the first generations of stars, offering insights into the evolution of the Milky Way. While 3I Atlas represents the infinite, C 2025 R2 SWAN embodies the delicate balance between permanence and transience within the solar system. Discovered on 11 September 2025 by Vladimir Bezugli using SHO's SWAN instrument, this comet's trajectory brought it perilously close to Earth, setting the stage for a potential meteor shower. Yet, like C 2025 F2, its fate hinges on the whims of solar radiation and gravitational forces. C 2025 R2's discovery was marked by a dramatic brightening from magnitude 11 to 6.2 in just a month, a phenomenon attributed to the Holecek effect, a temporary reduction in solar elongation that shielded it from observation until mid-September. By the time it emerged, its coma spanned 2 arc minutes, and its tail stretched 2 degrees across the sky. This sudden visibility captivated astronomers and stargazers alike, as the comet's peak magnitude of 6.9 made it visible in binoculars and even the naked eye under dark skies. Comets like C2025 F2, SWAN, 3I Atlas and C2025 R2, SWAN, are more than celestial curiosities. They are threads in the fabric of the universe, weaving together the histories of stars, planets, and life itself. Their journeys remind us that the cosmos is a dynamic, ever-changing realm, where creation and destruction are intertwined. From the disintegration of a fragile nucleus to the interstellar voyage of a cosmic wanderer, these comets challenge our understanding of the universe while grounding us in its vast, indifferent majesty. As humanity continues to peer into the abyss, we find not emptiness, but stories written in light and dust. Comets are the messengers of the void, carrying echoes of ancient worlds and glimpses of futures yet unwritten. In their fleeting brilliance, we glimpse the impermanence of our own existence and the enduring wonder of the cosmos. In the vast, endless expanse of the cosmos, where stars flicker like distant beacons and galaxies swirl in silent symphonies, comets emerge as transient messengers from the farthest reaches of the universe. These celestial wanderers, born of ice and dust, trace ephemeral arcs through the heavens, their glowing tails painting stories of distant origins. Among them, the comets of 2025 F2 SWAN, 3I Atlas, and C2025 R2 SWAN stand as testaments to the universe's capacity for surprise, mystery, and wonder. Their journeys, captured by human ingenuity and curiosity, offer glimpses into the fragile dance of cosmic forces and the fleeting nature of existence itself. C2025 F2 SWAN, discovered by the Solar and Heliospheric Observatory (SOHO) in late March 2025, was destined to shine briefly before vanishing into the void. Its trajectory, shaped by the gravitational tides of the inner solar system, brought it perilously close to the Sun, where it unraveled into a swirling cloud of debris. Meanwhile, 3I Atlas, an interstellar traveler, arrived from the depths of the Milky Way, its hyperbolic path defying the Sun's pull. This alien comet, rich in carbon dioxide and cyanide, carried secrets of a star system long vanished, offering a tantalizing glimpse into the chemistry of other worlds. And C2025 R2 SWAN, a more modest yet no less enigmatic visitor, emerged from obscurity to grace the night sky with a fleeting brilliance, its orbit hinting at a journey spanning millennia. Together, these comets weave a tapestry of cosmic phenomena, each thread a story of creation, destruction, and rebirth. To witness these celestial emissaries is to stand at the intersection of science and poetry. Their appearances challenge our understanding of the universe, reminding us that the cosmos is not a static realm, but a dynamic, ever-changing theater of motion and transformation. The comets of 2025 invite us to contemplate the impermanence of beauty, the fragility of life, and the infinite scale of the universe. As we embark on this exploration, we are not merely observers, but participants in a grand narrative, one that stretches across eons, binding humanity to the stars through the shared pursuit of knowledge and awe. The story of C2025 F2 SWAN begins in the cold, dark expanse of the outer solar system, where it slumbered for untold millennia. Discovered on 29 March 2025 by Vladimir Bezugli, Michael Matiasso, and Rob Matson, the comet was first detected in images captured by the solar wind anisotropies SWAN camera aboard the Solar and Heliospheric Observatory (SOHO). At the time of its discovery, the comet was a faint object, its apparent magnitude of 11 barely perceptible against the backdrop of the cosmos. Yet, within weeks, its brightness surged, a harbinger of the dramatic fate that awaited it. By 3 April 2025, the comet had brightened to magnitude 10.6, its coma surrounded by a tail stretching over 10 arc minutes, becoming visible in amateur telescopes. Observers marveled at its sudden luminosity, a phenomenon that seemed to defy the usual patterns of cometary behavior. The comet's trajectory, calculated from its orbital parameters, revealed a parabolic path, suggesting it was making its first and possibly final journey into the inner solar system. Its perihelion, the closest approach to the Sun, was projected to occur at a distance of 0.33 AU, placing it within the orbit of Mercury. Such proximity to the Sun would subject the comet to extreme temperatures and gravitational forces, conditions that could either amplify its brightness or hasten its demise. For a brief moment, hope flared among astronomers. The comet was expected to reach a peak magnitude of 5 by early May, bright enough to be visible to the naked eye. However, by mid-April, its brightening stalled, and by 22 April, it had disintegrated entirely, leaving behind only a diffuse cloud of dust and gas. The nucleus, once a solid core of ice and rock, had shattered under the Sun's relentless pull, its fragments scattering into the void. This disintegration was not a quiet collapse but a violent unraveling. The comet's outburst on 5 April marked the beginning of its end, a burst of energy that temporarily increased its brightness to magnitude 8.6. Observers noted the elongation of its tail, which stretched across the sky like a dying ember. The event underscored the precarious balance between a comet's internal cohesion and the external forces that govern its fate. The Sun's radiation, combined with tidal stresses from its gravitational field, proved too much for the comet to withstand. By the time it crossed the celestial equator in October 2025, it had faded into obscurity, its remnants destined to drift silently into the abyss. C-2025 F2 SWAN story is a poignant reminder of the universe's indifference to permanence. Its brief brilliance, captured in fleeting moments of observation, serves as a metaphor for the impermanence of all things. The comet's disintegration was not a failure, but a natural conclusion to its journey, a release of the tension between its icy heart and the Sun's fiery embrace. In its final days, it painted the sky with a ghostly glow, a testament to the fragile beauty of celestial phenomena. As its fragments dispersed, they joined the cosmic dust that drifts between the stars, a silent echo of a comet that once dared to shine. While C-2025 F2 SWAN met its fate in the Sun's grasp, another comet, 3I Atlas, embarked on a journey far stranger and more profound. Unlike the native comets of our solar system, 3I Atlas was not bound by the Sun's gravity. Instead, it followed a hyperbolic trajectory, a path dictated by a velocity so great that it could never return. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, stationed at Rio Hurtado, Chile, the comet entered the inner solar system at a speed of 58 kilometers per second, faster than any known interstellar object before it. This velocity, exceeding the Sun's escape speed, meant that 3I Atlas was not a visitor returning from the distant Oort cloud, but a true interloper from the vast expanse of interstellar space. The comet's origin, traced back to the direction of the constellation Sagittarius near the Milky Way's galactic center, hinted at a history stretching billions of years into the past. Unlike the previous interstellar objects, 1I Oumuamua and 2I Borisov, 3I Atlas bore the marks of a different kind of stellar system. Observations by the James Webb Space Telescope and the Hubble Space Telescope revealed a coma rich in carbon dioxide, a stark contrast to the water-dominant chemistry of solar system comets. This anomaly suggested that 3I Atlas had formed in an environment far colder and denser than the Kuiper Belt, perhaps in a protoplanetary disk where volatile ices remained frozen despite proximity to its host star. The presence of cyanide and nickel vapor in its coma added another layer of intrigue, pointing to a complex chemical evolution that defied the neat categorization of cometary science. As 3I Atlas neared its closest approach to the Sun on 29 October 2025, its activity intensified. The Sun's heat caused its nucleus to sublimate, releasing jets of gas and dust that sculpted its coma into a diffuse reddish haze. Unlike the familiar greenish-blue halos of solar system comets, 3I Atlas's coma bore a hue reminiscent of interstellar dust clouds, a visual echo of its extraterrestrial provenance. The comet's trajectory, with an orbital eccentricity of 6.14, ensured that it would depart the solar system as swiftly as it arrived, carrying with it the secrets of a distant star system. By the time it passed Mars in October 2025 and Jupiter in March 2026, It would leave no trace of its passage except in the records of those who had watched its fleeting journey across the heavens. Yet 3I Atlas was not merely a visitor, it was a messenger. Its chemical signature, its hyperbolic path, and its age, estimated at billions of years, offered a rare opportunity to glimpse the diversity of planetary systems beyond our own. What had shaped this interstellar wanderer? Had it once orbited a long-dead star, now adrift in the cosmic tide? Or was it a fragment of a primordial world, ejected in the chaotic youth of its birthplace? The answers lay hidden in the data, waiting to be unraveled by those who sought to understand the universe, not just as it is, but as it once was, and as it might yet become. The composition of 3I Atlas is a cosmic puzzle, one that challenges our assumptions about the uniformity of planetary systems and the building blocks of life. While solar system comets are often characterized by their abundance of water ice, ammonia, and methane, 3I Atlas stands apart with its strikingly high concentration of carbon dioxide. This divergence suggests that the comet formed in an environment vastly different from the Kuiper belt or the Oort cloud. In our solar system, carbon dioxide is a minor component of cometary material, typically found in trace amounts alongside water and other volatiles. Yet in 3I Atlas, CO2 dominates, hinting at a formation process that occurred in a region where temperatures were consistently low enough to preserve such volatile compounds in solid form. This implies that 3I Atlas may have originated in a protoplanetary disk, where the frost line, the boundary beyond which volatile compounds freeze, extended much farther from its host star than in our own system. In such a scenario, the comet's icy nucleus would have accumulated carbon dioxide-rich ices, locked in place by the cold vacuum of space. The presence of cyanide in its coma adds another layer of complexity. Cyanide, a molecule essential to the synthesis of amino acids and nucleobases, is not uncommon in the universe, but its detection in 3I Atlas raises intriguing questions about the role of such compounds in interstellar chemistry. Was this comet a crucible for prebiotic reactions? Did the cyanide originate from the comet's parent star system, or was it acquired through interactions with the interstellar medium? The answers lie buried in the comet's history, a history that spans eons and traverses the vast distances between stars. The James Webb Space Telescope's observations of 3I Atlas revealed not only carbon dioxide and cyanide, but also the faint traces of water ice and carbon monoxide, a combination that further underscores the comet's uniqueness. The scarcity of water compared to its native counterparts suggests that 3I Atlas's home system experienced a different evolutionary path, one where water was either less abundant or more readily lost to space. This discrepancy challenges the prevailing notion that planetary systems across the galaxy follow a common blueprint, built from the same primordial materials. Instead, it hints at a universe where diversity reigns supreme, where the raw ingredients for life may take countless forms, each shaped by the idiosyncrasies of its stellar cradle. As 3I Atlas continued its journey through the inner solar system, its chemical signature remained a subject of intense scrutiny. The comet's coma, illuminated by the sun's rays, glowed with a reddish hue, a visual manifestation of the dust and gases that had been released from its nucleus. Spectroscopic analyses conducted by the Very Large Telescope and the Hubble Space Telescope confirmed the presence of nickel vapor, a metal typically associated with the cores of differentiated bodies. The detection of nickel in an interstellar comet was unprecedented, raising questions about the internal structure of 3I Atlas and the processes that governed its formation. Had it once been part of a larger body, shattered by collisions in the distant past? Or did its nucleus harbor metallic inclusions from the earliest days of its parent system? Each discovery about 3I Atlas deepens the mystery of its origins. The comet is not just a relic of another star system. It is a time capsule, carrying the imprint of a cosmic history we have yet to fully comprehend. As it hurtled toward perihelion, its chemical profile offered a rare opportunity to study the composition of an interstellar object in exquisite detail. The data collected from 3I Atlas would provide invaluable insights into the diversity of planetary system and the potential for life beyond our own. In the coming months, as the comet departed the solar system, its legacy would endure, not as a fleeting visitor, but as a beacon of possibility, a reminder that the universe is not a monolith, but a tapestry woven from an infinite array of possibilities. The age of 3I Atlas is a window into the vast temporal scales that govern the cosmos. a chronicle of epochs stretching back billions of years. Unlike the comets that originate within our solar system, which are bound by its 4.6 billion year history, 3I Atlas carries with it the imprint of a much older universe. Studies of its hyperbolic excess velocity and orbital trajectory suggest that the comet has traveled across the Milky Way for an astonishing duration, possibly as long as 14 billion years. This places its origins in an era when the Milky Way itself was still in its infancy, a time when the first stars and planetary systems were coalescing from the primordial cosmic soup. To grasp the significance of this, one must imagine a universe teeming with nascent stars, their light flickering across the darkness, each one a cradle for worlds yet to be born. The implications of 3I Atlas's age extend far beyond its immediate physical properties. If the comet indeed hails from the thick disk of the Milky Way, a population of ancient stars with lower metallicities than our own Sun, it may represent a relic from an earlier phase of galactic evolution. The thick disk, believed to be the oldest component of the Milky Way, predates the thin disk where our solar system resides by billions of years. The presence of 3I Atlas in this region suggests that it formed in a stellar nursery where the conditions were drastically different from those that shaped our own planetary system. In such an environment, the chemical composition of planetary materials would have varied significantly, giving rise to a diverse array of planetary bodies. Some of these may have been ejected into the interstellar void, becoming solitary travelers like 3I Atlas, forever drifting through the cosmos. Tracing the comet's trajectory backward in time reveals a path that intersects with some of the most transformative events in the history of the universe. Over the course of its journey, 3I Atlas would have traversed regions of the Milky Way, where massive stars were born and died in cataclysmic supernova explosions, enriching the interstellar medium with heavier elements. These stellar furnaces forged the building blocks of planets and life itself, scattering their products across the galaxy. It is conceivable that 3I Atlas absorbed some of this enriched material during its travels, incorporating it into its icy nucleus. The presence of carbon dioxide and cyanide in its coma may be a direct consequence of this cosmic recycling, a testament to the interconnectedness of stellar evolution and planetary formation. Yet the comet's age also raises profound questions about the longevity of planetary systems. If 3I Atlas has survived for billions of years, what does this imply about the stability of the environments in which it was born? Could other interstellar objects like 3I Atlas have similarly endured the test of time, preserving the secrets of their origins in their frozen nuclei? The answer may lie in the study of future interstellar visitors, each one a potential messenger from a forgotten epoch. As 3I Atlas continues its journey through the solar system, its trajectory serves as a reminder that the universe is not only vast in space, but also immense in time, a continuum where the past and present converge in the silent dance of celestial objects. The discovery of 3I Atlas compels us to reconsider our understanding of cosmic timelines. The universe, with its 13.8 billion year history, is a repository of countless stories, each one etched into the fabric of space-time. 3I Atlas is one such story, a testament to the resilience of matter against the relentless passage of time. As it departs the solar system, its legacy endures, not as a mere interstellar wanderer, but as a bridge between the ancient past and the unfolding future of the cosmos. In its journey, we find a reflection of our own quest for knowledge, a reminder that the universe is not just a place to explore, but a timeless narrative in which we are privileged to play a fleeting role. As 3I Atlas hurtles through the inner solar system, its trajectory weaves a delicate web of gravitational influences, brushing past the planets in a dance choreographed by celestial mechanics. Though it will not pose a threat to Earth, the comet's journey brings it into the gravitational sphere of Mars, Venus and Jupiter planets, whose own histories are intertwined with the evolution of the solar system. On 3 October 2025, 3I Atlas will pass within 0.19 AU of Mars, a distance that, while vast in human terms, is remarkably close in astronomical scales. This encounter will provide an opportunity for Martian orbiters to study the comet in detail, capturing data on its activity and composition as it approaches perihelion. The red planet, with its thin atmosphere and barren surface, may offer a vantage point from which to observe the comet's interaction with solar radiation, a phenomenon that shapes the behavior of all comets in the inner solar system. By 3 November 2025, 3I Atlas will pass 0.65 AU from Venus, a planet whose thick atmosphere and runaway greenhouse effect have long fascinated scientists. Though the comet will not interact directly with Venus's dense cloud layers, its passage through the inner solar system will allow astronomers to compare its behavior with that of comets that have ventured closer to the Sun. The data collected during this phase will shed light on the comet's thermal response to solar heating, revealing how its volatile ices respond to the extreme conditions of the inner solar system. On 19 December 2025, 3I Atlas will pass 1.80 AU from Earth, a distance sufficient to prevent any gravitational perturbations, but close enough to allow continued observations from ground-based and space-based telescopes. From this vantage point, astronomers will monitor the comet's fading glow as it begins its slow retreat from the Sun, its activity diminishing as it moves beyond the reach of solar influence. Perhaps the most significant planetary encounter occurs on 16 March 2026, when 3I Atlas will pass within 0.36 AU of Jupiter. The gas giant's immense gravitational field will exert a subtle but measurable influence on the comet's trajectory, altering its path by a fraction of a degree. This encounter, though brief, will serve as a final act in the comet's solar system journey, shaping its future course as it returns to the interstellar void. The gravitational tug from Jupiter will not be enough to trap 3I Atlas within the solar system, but it will impart a slight change in its velocity, ensuring that it will not return for eons if ever. These planetary encounters are more than mere milestones in 3I Atlas's journey. They are windows into the intricate web of gravitational interactions that govern the motions of celestial bodies. Each encounter, no matter how brief, contributes to the comet's evolution, influencing its activity and trajectory in ways that will be studied for decades to come. As 3I Atlas departs the solar system, it leaves behind a trail of data, a record of its passage that will help scientists refine their understanding of interstellar objects and the forces that shape their journeys through the cosmos. In this dance of planets and comets, we find a reflection of the universe's grand design, an intricate ballet of motion and transformation that binds the smallest grains of cosmic dust to the largest celestial bodies in a single eternal rhythm. Amid the celestial tapestry of 2025, C2025 R2 SWAN emerged as a fleeting beacon, its light illuminating the night skies before vanishing into the void. Discovered on 11 September 2025 by Vladimir Bezugli through the Solar and Heliospheric Observator SWAN instrument, the comet arrived in the inner solar system with a quiet intensity, its journey marked by rapid transformation and uncertain fate. Unlike the interstellar wanderer 3I Atlas, C2025 R2 SWAN was a native of our cosmic neighborhood, its orbit shaped by the gravitational tides of the Sun and planets. Yet, its path was no less remarkable, a trajectory that brought it perilously close to the Sun and positioned it for a rare celestial encounter with Earth. The comet's initial observations revealed a modest brightness, with an apparent magnitude of 7.4 at the time of discovery. However, within weeks, its luminosity surged dramatically, peaking at magnitude 6.2 on 16 September 2025. This rapid brightening was attributed to the comet's sudden emergence from the Holechek effect, a period during which it had been less than 30 degrees from the Sun, rendering it invisible to most telescopes. As it broke free from the Sun's glare, the comet's coma expanded, its tail stretching across the sky like a brushstroke of light. Observers in the southern hemisphere, where the comet reached its highest altitude in the evening sky, reported seeing it with 50mm binoculars, a rare treat for amateur astronomers. C2025 R2 SWAN's trajectory was one of extremes. It reached perihelion, the closest point to the Sun, on 12 September 2025, at a distance of 0.5 AU, placing it within the orbit of Mercury. The Sun's intense radiation and gravitational forces subjected the comet to extreme conditions, accelerating the sublimation of its volatile ices and releasing jets of gas and dust that sculpted its coma into a diffuse shimmering halo. The comet's closest approach to Earth occurred on 19 October 2025 at a distance of 0.26 AU, bringing it within striking range of our planet. This encounter raised the possibility of a meteor shower, as the comet's debris stream intersected Earth's orbit. While no major meteor storm was expected, the event highlighted the dynamic relationship between comets and terrestrial planets, a connection that has played a pivotal role in shaping the history of our world. The comet's orbit, though not yet fully determined due to the limited observation arc, suggested a long-period trajectory with an estimated orbital period ranging from 1400 to 20,000 years. This ambiguity reflected the challenges of tracking objects that spend most of their existence in the distant reaches of the solar system, where they are nearly impossible to detect. The Minor Planet Center and the Jet Propulsion Laboratory (JPL) offered conflicting estimates for the comet's orbital period, underscoring the difficulty of predicting the paths of long-period comets. Despite these uncertainties, the comet's journey through the inner solar system provided valuable data, helping scientists refine their models of cometary dynamics and the distribution of icy bodies in the outer solar system. As C-2025 R2 SWAN continued its journey, its future remained shrouded in uncertainty. Would it survive its close encounter with the Sun? Or would it succumb to the same fate as C-2025 F2 SWAN, disintegrating into a cloud of dust and gas? The comet's fate was a reminder of the delicate balance between preservation and destruction, a balance that governed the lives of all celestial wanderers. In its brief brilliance, C-2025 R2 SWAN served as a fleeting reminder of the universe's impermanence, a luminous echo of the cosmic forces that shape and reshape the heavens. In the vast expanse of the universe, where time stretches into eternity and space curves in ways we barely comprehend, comets emerge as enigmatic messengers. They are wanderers of the solar system, fragments of primordial material, flung into the void by the gravitational dance of distant worlds. Among the countless celestial bodies that populate the night sky, comets hold a special place, not only for their ethereal beauty, but for the profound insights they offer into the origins of our cosmic neighborhood. Three remarkable comets, C-2025 F2 SWAN, 3I Atlas and C-2025 R2 SWAN, each tell a story of transience, transformation, and the ceaseless passage of time. C-2025 F2 SWAN was once a glimmer of hope, a celestial visitor that briefly brightened the skies before succumbing to the forces of entropy. Discovered by the Solar and Heliospheric Observatory's SWAN instrument, this comet followed a path that brought it perilously close to the Sun, only to disintegrate before reaching its closest approach. Its brief moment of brilliance serves as a poignant reminder of the delicate balance between creation and destruction in the cosmos. Meanwhile, 3I Atlas stands apart as an interstellar traveler, a rare object born beyond the confines of our solar system. Its hyperbolic trajectory and ancient origins mark it as a relic from the galactic past, carrying with it the secrets of a time when the Milky Way was young. Unlike C-2025 F2, 3I Atlas will never return to our neighborhood, making its fleeting passage all the more precious. Then there is C-2025 R2 SWAN, a more recent arrival that defies expectations. Emerging from the shadows near the Sun, it shines with a luminous tail stretching across the night sky, visible even to backyard observers. Its discovery highlights the role of modern technology in uncovering the hidden wonders of the universe, while its potential to produce a meteor shower underscores the interconnectedness of celestial phenomena. Together, these three comets weave a narrative of cosmic duality, of beginnings and endings, of journeys both eternal and ephemeral. Through their stories, we glimpse the vastness of space and the mysteries that lie beyond our current understanding. As we embark on this journey through the lives of these comets, we are reminded of the universe's grandeur and the fleeting nature of existence. Each comet is a whisper from the void, a fleeting beacon in the darkness, urging us to look beyond the familiar and seek the truths hidden in the cosmos. What they reveal about the universe and ourselves is a question that echoes through the stars. The story of C-2025 F2 SWAN began in the quiet depths of space, where it drifted unseen until it was captured in images taken by the Solar and Heliospheric Observatory's SOHO Solar Wind Anisotropies (SWAN) instrument. Discovered in late March 2025, the comet was first identified by astronomers Vladimir Bezugli, Michael Matiasso, and Rob Matson, who noticed a faint glowing object in the Lyman ARV images taken on 29 and 31 March. At the time of its discovery, C2025 F2 was approximately 1.62 astronomical units (AU) from Earth and 0.92 AU from the Sun, with a solar elongation of 28 degrees. Its initial apparent magnitude was around 11, placing it just beyond the reach of casual observers, but within the purview of dedicated astronomers. The comet's trajectory brought it steadily toward the inner solar system, following a path that would take it to perihelion, the closest point in its orbit to the Sun, on an expected date in May 2025. Astronomers eagerly anticipated its evolution, hoping that it would brighten significantly as it neared the Sun, potentially becoming visible to the naked eye under optimal conditions. Initial predictions suggested that C2025 F2 would reach a peak magnitude of about 5, making it a binocular or even naked eye object. However, as April progressed, the comet's behavior deviated from expectations. Instead of continuing to brighten, it began to fade, signaling that something was amiss. By early April, C2025 F2 had reached a magnitude of 10.6, and observations revealed the emergence of a faint tail stretching about 10 arc-minutes in length. Just hours later, astronomer Kelvin Yoshimoto recorded an image showing a much longer tail, measuring 35 arc-minutes. The comet's appearance continued to evolve, with visual observations from Mike Meyer on April 4 estimating its magnitude at 9.2, noting its resemblance to a well-concentrated globular cluster. The following day, an outburst occurred, causing the comet to brighten dramatically. On April 6, images by T-USA captured the comet at an apparent magnitude of 8.6, while visual observers estimated it at 8.1 to 8.3. The tail, now spanning 1.5 degrees, stretched across the sky like a spectral ribbon, a testament to the comet's dynamic nature. Despite these signs of activity, the comet's fate was sealed. By mid-April, its brightness had begun to decline, and astronomers observed that it was disintegrating. The nucleus, once a cohesive body of ice and rock, had started to break apart, leaving behind a diffuse cloud of dust and debris. The disintegration process accelerated, and by April 22, the nucleus had completely vanished, replaced by a temporary brightening of the surrounding dust cloud. The comet's remnants continued to move through the inner solar system, shifting from the morning sky to the evening sky, where it passed near the Pleiades in May, before venturing southward. Though it faded from view, C2025 F2 left behind a trail of scientific inquiry, offering clues about the fragile nature of cometary bodies and the forces that govern their fates. The comet's orbital path traced a nearly parabolic trajectory, suggesting that it originated from the outer reaches of the solar system, perhaps from the distant Oort cloud. Calculations based on its motion indicated that it had spent the last 40,000 years traveling inward from a distance of approximately 3,750 AU, over 561 billion kilometers, before beginning its final approach toward the Sun. After reaching perihelion at a distance of 0.333 AU, just inside the orbit of Mercury, the comet's trajectory shifted outward, carrying it back into the cold expanse of space. Its journey had been brief but revealing, a fleeting encounter with the Sun that ultimately led to its dissolution. Through the observations of C2025 F2 SWAN, astronomers gained valuable insights into the life cycle of comets and the conditions that lead to their disintegration. While the comet itself was lost, its legacy endures in the data it left behind, a record of a celestial traveler that danced briefly with the light before vanishing into the void. Among the many celestial wanderers that traverse the solar system, few possess the distinction of being truly interstellar in origin. 3I Atlas, discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, stationed at Rio Hurtado, Chile, is one such anomaly. Unlike the vast majority of comets that originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas follows an unbound hyperbolic trajectory, meaning it is not gravitationally bound to the Sun, and will eventually escape the solar system entirely. With a hyperbolic excess velocity of 58 kilometers per second, the comet is moving at a speed far greater than any native solar system object, ensuring its departure from our cosmic neighborhood. This places it in a rare category of interstellar visitors, joining the ranks of 1I Oumuamua and 2I Borisov as the third confirmed interstellar object to have traversed the inner solar system. The discovery of 3I Atlas marked a significant milestone in the study of interstellar objects, providing scientists with an unprecedented opportunity to examine material from beyond the solar system. Initial observations revealed that the comet was actively producing a coma, a cloud of gas and dust, expelled from its nucleus. As it approached the Sun, the nucleus itself remains shrouded in mystery, as its exact size is difficult to determine due to the overwhelming brightness of the coma. However, estimates derived from observations by the Hubble Space Telescope suggest that the nucleus has a diameter ranging between 0.32 and 5.6 kilometers, with the most probable value being less than 1 kilometer. This relatively small size implies that 3I Atlas is a fragile object, susceptible to rapid disintegration, as it is subjected to the intense heat and radiation of the inner solar system. One of the most intriguing aspects of 3I Atlas is its chemical composition, which offers a glimpse into the conditions of its birthplace. Spectroscopic analysis conducted by the James Webb Space Telescope, JWST, and other observatories have revealed an unusual abundance of carbon dioxide in its coma, alongside traces of water ice, water vapor, carbon monoxide, and carbonyl sulfide. Additionally, the Very Large Telescope detected the presence of cyanide gas and atomic nickel vapor, substances commonly associated with cometary activity in the solar system. These findings raise compelling questions about the nature of the star system from which 3I Atlas originated. If its composition differs significantly from that of solar system comets, it could indicate that the comet formed in an environment with distinct chemical conditions, perhaps in a different galactic region or under varying stellar influences. The trajectory of 3I Atlas is equally extraordinary. Its orbital eccentricity of 6.14 and 0.002 is the highest among known interstellar objects, making its path appear almost linear rather than curved. This extreme eccentricity means that 3I Atlas's approach to the solar system was not a gentle drift, but a high-speed passage through the inner solar system. Its closest approach to the Sun, or perihelion, will occur on 29 October 2025 at a distance of 1.36 AU, placing it between the orbits of Earth and Mars. Despite this relatively modest distance, the comet will not pose a threat to Earth, as its closest approach to our planet will be 1.8 AU, well outside the range of potential impact. The comet's retrograde inclination of 5 dwarf relative to the ecliptic further distinguishes it from the majority of solar system objects, adding to the intrigue of its interstellar origin. As 3I Atlas continues its journey through the solar system, it will pass in close proximity to several planets, including Venus, Mars, and Jupiter. These encounters, while not direct collisions, will provide additional opportunities for observation and data collection. The comet will pass within 0.19 AU of Mars on 3 October 2025, a distance close enough to be studied in detail by orbiting spacecraft. Following perihelion, it will approach Venus at a distance of 0.65 AU on 3 November 2025, before continuing its escape from the solar system. By 19 December 2025, it will be 1.8 AU from Earth, and by 16 March 2026, it will pass 0.36 AU from Jupiter. These interactions with the solar system's gravitational giants will subtly alter its trajectory, but the comet will ultimately retain its hyperbolic path, ensuring its eventual departure from our cosmic vicinity. The study of 3I Atlas represents a rare and invaluable window into the interstellar realm. As it travels through the inner solar system, scientists will continue to monitor its evolution, seeking to unravel the mysteries of its origin and composition. With each new observation, we gain a deeper understanding of the vast and diverse nature of the cosmos, reinforcing the idea that our solar system is but one thread in the immense fabric of the universe. Amid the ever-changing tapestry of the night sky, C-2025 R2 SWAN emerged as a celestial enigma, a comet that defied expectations and illuminated the heavens with a sudden burst of brilliance. First spotted on 11 September 2025 by amateur astronomer Vladimir Bezugli through the solar wind anisotropes, SWAN, instrument aboard the Solar and Heliospheric Observatory, SOHO. The comet was initially a subtle presence in the Lyman-Arve images that SOHO routinely captures. As the days passed, its visibility increased, and by the time it was confirmed, it had already brightened to an apparent magnitude of 7.4, with a tail stretching approximately 2 degrees across the sky. This rapid evolution, from obscurity to prominence, marked C2025 R2 as a fascinating object for both professional and amateur astronomers alike. The comet's initial discovery was complicated by its proximity to the Sun. For much of August and early September, C2025 R2 remained within 30 degrees of the solar disk, making it difficult to observe directly. This period of concealment meant that the comet was not detected earlier despite its growing brightness, a phenomenon known as the Holacek effect, where comets near the Sun are often obscured by the glare of daylight. However, as it moved farther from the Sun, its visibility improved, and it became detectable in optical telescopes and even in binoculars. By early September, C2025 R2 had brightened to a magnitude of 8, and by 16 September, it reached a peak of 6.2, making it accessible to observers equipped with modest instruments. What sets C2025 R2 apart from other comets was not only its rapid brightening, but also its potential for future visibility. Projections suggested that it could reach a magnitude of 4 by late October 2025, when it would be at its closest approach to Earth. This would place it among the brighter comets of the year, rivaling the expected brightness of C2025 A6, Lemon, during the same period. The comet's trajectory carried it through the constellation Virgo, where it passed near the prominent star Spica, enhancing its visibility for observers in the southern hemisphere. Its position in the sky, combined with its increasing luminosity, made it a prime candidate for widespread observation and study. Beyond its immediate observational appeal, C2025 R2 offered valuable insights into the dynamics of cometary behavior. Its orbit brought it to perihelion, one day after its discovery, on 12 September 2025 at a distance of 0.5 AU from the Sun, placing it well within the orbit of Venus. This close approach to the Sun subjected the comet to intense solar radiation, triggering the sublimation of its icy nucleus and the release of gas and dust that formed its luminous coma and tail. The process of outgassing was particularly pronounced in the days following its perihelion, as the comet's activity intensified, resulting in a dramatic increase in brightness. The comet's orbital characteristics presented an intriguing puzzle for astronomers. While its perihelion distance was well established, determining its overall orbital period proved more challenging. Observations from the Solar and Heliospheric Observatory, SOHO, and the Stereo AMPERS spacecraft provided limited data due to the comet's proximity to the Sun, leaving uncertainty about its aphelion distance and the full extent of its orbit. Estimates varied widely, with some models suggesting an orbital period of approximately 1,400 years, and others extending to 20,000 years. This ambiguity underscored the complexity of predicting cometary paths, especially for objects that appear suddenly and undergo rapid changes in brightness and activity. As C2025 R2 continued its journey through the inner solar system, it remained a subject of fascination for the global astronomical community. Its potential to produce a meteor shower as Earth crossed its orbit on 5 October 2025 added an extra layer of interest, as such events are rare and provide valuable data on the composition of cometary debris. The comet's path also brought it into the celestial equator on 3 November 2025, a transition that would enhance its visibility for observers across the globe. Whether it would continue to shine brightly or fade into obscurity remained an open question. But one thing was certain: C2025 R2 had already etched its mark on the annals of astronomical discovery. The disintegration of C2025 F2 SWAN serves as a poignant reminder of the delicate balance that governs cometary survival. Unlike asteroids, which are composed primarily of rock and metal, and can endure for millions of years, comets are fragile constructs of ice, dust, and volatile compounds. As they approach the Sun, the intense heat causes their surfaces to sublimate, releasing gas and dust in a process that forms the characteristic coma and tail. While this activity can create breathtaking displays in the night sky, it also renders comets vulnerable to structural failure. In the case of C2025 F2, The combination of solar heating and internal stresses led to its gradual breakdown, culminating in the complete disintegration of its nucleus by mid-April 2025. This event underscores the unpredictable nature of cometary evolution. Prior to its discovery, C2025 F2 was expected to reach a peak magnitude of 5, making it visible to the naked eye under dark skies. However, the unexpected outburst observed in early April, followed by a rapid decline in brightness, indicated that the comet was undergoing structural instability. Such fluctuations are not uncommon in comets, but the swift disintegration of C2025 F2 highlights the fragility of these celestial bodies. The fact that its nucleus vanished within a matter of weeks, leaving behind only a diffuse cloud of dust and debris, illustrates the fine line between a vibrant celestial display and an ephemeral cosmic whisper. Studying such events provides crucial insights into the physical properties of comets and the mechanisms that govern their disintegration. One of the primary factors influencing a comet's longevity is its composition. Volatile-rich nuclei, composed largely of water ice, carbon dioxide, and other frozen gases, tend to be more susceptible to rapid sublimation and fragmentation. In contrast, comets with denser, more stable structures can withstand solar heating for longer periods. The disintegration of C2025 F2 suggests that its nucleus was particularly fragile, perhaps due to a high concentration of volatile materials or an inherently weak internal structure. Understanding these factors allows astronomers to refine models of cometary behavior and improve predictions regarding their visibility and lifespan. Moreover, the fate of C2025 F2 raises intriguing questions about the broader distribution of cometary material in the solar system. While the remnants of the comet will gradually disperse, some of its dust and ice may interact with planetary atmospheres, contributing to meteor showers or altering atmospheric chemistry. Over time, these particles will be swept away by the solar wind or incorporated into larger bodies such as asteroids and planetary rings. The transient nature of comets, therefore, plays a subtle yet significant role in shaping the cosmic environment, reminding us that even the smallest celestial bodies can leave lasting imprints on the universe. The story of C2025 F2 SWAN is not merely one of loss, but also of transformation. In its final moments, the comet released a cascade of dust and gas, a silent farewell that will echo through space for millennia. Its disintegration serves as a reminder of the impermanence that defines much of the cosmos, a stark contrast to the seemingly eternal stars that dot the night sky. Yet, even in its demise, C2025 F2 contributes to the ongoing cycle of cosmic renewal, its remnants dispersing into the vast expanse of space, where they may one day give rise to new celestial phenomena. As we observe the remnants of C2025 F2 drifting away, we are reminded that comets are not simply visitors from the outer reaches of the solar system. They are storytellers, each one bearing the marks of its journey through time and space. Their fragile natures force us to confront the reality that even the most awe-inspiring celestial displays are fleeting, shaped by the same forces that govern the birth and death of stars. In this way, the disintegration of C2025 F2 is not an end, but a continuation of the universe's ceaseless transformation, a testament to the intricate dance of creation and destruction that defines our cosmic home. Among the celestial wanderers that traverse the solar system, 3I Atlas stands apart not only for its interstellar origin, but for the profound implications of its ancient lineage. By tracing its trajectory and analyzing its velocity vectors, astronomers have estimated that 3I Atlas may be between 3 and 14 billion years old, an age that places it firmly in the distant past of the Milky Way. If the comet indeed hails from the galaxy's thick disk, a region populated by some of the oldest stars in our galactic neighborhood, it could predate the formation of the solar system by billions of years. This staggering antiquity transforms 3I Atlas from a mere interstellar visitor into a relic of a bygone era, a fragment of the cosmic past that has survived the eons to arrive at our doorstep. The thick disk of the Milky Way is a region of profound historical significance, containing stars that formed during the early stages of the galaxy's evolution. Unlike the younger metal-rich stars of the thin disk, thick disk stars are characterized by their lower metallicity and higher velocities, indicating that they have spent much of their existence in the chaotic gravitational tides of the galactic center. If 3I Atlas originated from this ancient stellar population, it may have formed in an environment vastly different from the one that gave rise to our own solar system. The conditions that shaped its icy nucleus and volatile composition could offer critical insights into the primordial materials that existed before the birth of the Sun, shedding light on the chemical and physical processes that governed the early universe. Studying 3I Atlas is akin to opening a sealed container of cosmic history, a time capsule that carries the signatures of a distant epoch. Its composition, as revealed by observations from the James Webb Space Telescope and other instruments, suggests that it is rich in carbon dioxide and contains trace amounts of water ice, carbon monoxide, and other volatile compounds. These findings raise intriguing questions about the chemical makeup of its parent star system and the environmental conditions under which it formed. If 3I Atlas originated in the thick disk, its composition could reflect the chemical diversity of the early Milky Way, where the first generations of stars forged the building blocks of planets and life. In this context, 3I Atlas is not just an interstellar object. It is a messenger from the past, carrying with it the echoes of a time when the galaxy was young and the universe was still taking shape. The implications of 3I Atlas's age extend beyond its chemical composition to the broader understanding of galactic evolution. The fact that an object as old as 3I Atlas has traveled across interstellar space and entered our solar system reinforces the idea that the Milky Way is a dynamic and ever-changing entity, where gravitational interactions and stellar migrations continually redistribute material across vast distances. The presence of such an ancient comet in our cosmic neighborhood suggests that the galaxy is a vast reservoir of primordial material, some of which may have played a role in the formation of planetary systems like our own. By studying 3I Atlas, astronomers can piece together the complex history of the Milky Way, tracing the movements of interstellar objects and their influence on the evolution of stars and planetary bodies. As 3I Atlas continues its journey through the inner solar system, its fleeting passage offers a rare opportunity to examine the remnants of a bygone era. The data gathered from its trajectory, composition, and activity will provide invaluable insights into the nature of interstellar comets and their potential role in shaping the early universe. In its silent flight through the void, 3I Atlas carries the weight of cosmic memory, a testament to the enduring connection between the past and the present, between distant stars and the fleeting beauty of a comet's glow. The fates of 3I Atlas and C2025R2 SWAN stand as striking contrasts, embodying the paradox of transience and permanence that defines the universe. While 3I Atlas, an interstellar traveler from the distant past, is destined to escape the solar system and vanish into the void, C2025R2 remains tethered to the gravitational pull of the Sun, its fate still uncertain. These divergent trajectories speak to the fundamental duality of cosmic existence, where some entities are bound to fleeting moments of brilliance, while others carry the weight of eternity across the vast expanse of space. C2025R2 SWAN, though recently discovered, has already demonstrated a remarkable capacity for change. Its rapid brightening in the weeks following its perihelion, coupled with the possibility of producing a meteor shower as Earth crosses its orbit, highlights the dynamic and unpredictable nature of comets. Even as it continues to evolve, its ultimate destiny remains unclear. Will it persist as a visible spectacle in the night sky, or will it too succumb to the forces that have undone so many before it? The answer may lie in the delicate balance between solar radiation and internal structural integrity, a balance that determines whether a comet endures or is reduced to a cloud of dust and gas. If it does disintegrate, its remnants will join the countless particles that drift through the solar system, a silent testament to the impermanence of celestial bodies. In contrast, 3I Atlas is a traveler of permanence, a cosmic nomad that will never return to the inner solar system. Its hyperbolic trajectory ensures that it will escape the Sun's gravitational grasp, continuing its journey across interstellar space for eons to come. Unlike C2025R2, which may one day fade into obscurity, 3I Atlas will persist as a witness to the vastness of the universe, a solitary voyager carrying with it the echoes of a distant past. The fact that it may be older than the solar system itself adds a layer of profound significance to its passage. It is a relic of an ancient time, a fragment of the Milky Way's earliest days that has endured the trials of cosmic travel to arrive at this moment in history. Yet for all its permanence, 3I Atlas is not immune to the forces of entropy. As it moves beyond the reach of the Sun, its activity will diminish, and its coma will dissipate, leaving behind only a cold, dark nucleus adrift in the void. In this way, even the most enduring comets are subject to the inexorable march of time. The difference lies in their scale of permanence. While 3I Atlas will persist for millennia, its presence will be known only to the instruments that track its path, whereas C2025 R2 may yet leave a more immediate and tangible imprint on the world through the meteor shower it could generate. These contrasting fates invite contemplation of the broader cosmic order, where creation and destruction exist in an eternal cycle. Every comet, whether it meets a dramatic end or continues its journey through the stars, plays a role in this grand interplay of forces. Some, like C2025 F2, vanish in a final burst of brilliance, their remnants scattering into the winds of space. Others, like 3I Atlas, endure as silent travelers, bearing witness to the vastness of the cosmos. And then there are those like C2025 R2, whose destinies remain uncertain, their futures shaped by the delicate balance between survival and dissolution. As we gaze upon these celestial wanderers, we are reminded that the universe is not static but ever-changing, a vast and intricate dance of motion. Comets in all their fleeting beauty serve as reminders of our own impermanence and the boundless possibilities that lie beyond the horizon of our understanding. Whether they endure or vanish, they are part of a greater story, one that stretches across time and space, connecting the past, present, and future in a continuous unfolding narrative. Comets are more than fleeting spectacles in the night sky. They are cosmic chronicles, carrying with them the imprints of the past and the seeds of the future. The stories of C2025 F2 SWAN, 3I Atlas, and C2025 R2 SWAN exemplify the diverse ways in which these celestial bodies shape our understanding of the universe. Each comet, in its own manner, bridges the gap between the known and the unknown, offering glimpses into the origins of our solar system, the vastness of interstellar space, and the intricate dance of celestial mechanics. Their discoveries and evolutions remind us that the universe is not a fixed entity, but a living, breathing expanse, constantly evolving and revealing new layers of complexity. The transient nature of comets compels us to appreciate the impermanence of all things, even as they illuminate the vastness of space. C2025 F2's disintegration serves as a poignant reminder that beauty and fragility often coexist, and that even the most radiant celestial displays are bound by the laws of physics. Yet in their passing, comets contribute to the cosmic cycle, their remnants dispersing into the solar system and influencing the environments of planets and moons. The potential for C2025 R2 to generate a meteor shower underscores this notion, as the dust and debris it leaves behind may one day fall to Earth, carrying with them the echoes of its journey through the void. These particles, though minute, are part of a grand continuum, linking the past to the future in a continuous exchange of matter and energy. 3I Atlas, on the other hand, embodies the enduring mystery of the cosmos. As an interstellar object with an estimated age of billions of years, it represents the distant past of the Milky Way, a time when the galaxy was young, and the conditions for planetary formation were vastly different from today. Its composition and trajectory offer invaluable clues about the early universe, providing insights into the chemical and physical processes that shaped the first generations of stars and planetary systems. By studying 3I Atlas, we gain a deeper appreciation for the interconnectedness of celestial bodies, recognizing that even the most isolated objects in the universe share a common heritage. The study of comets also reflects humanity's enduring quest for knowledge, a desire to understand the forces that govern the cosmos and our place within it. Each discovery expands our horizons, challenging existing theories and prompting new questions. The ability to observe and analyze these celestial visitors is a testament to the power of human ingenuity and the relentless pursuit of discovery. As we continue to refine our instruments and techniques, we inch closer to unraveling the mysteries that comets hold, bringing us ever nearer to a comprehensive understanding of the universe. In the grand tapestry of the cosmos, comets are both fleeting and eternal, their stories woven into the fabric of space and time. They remind us that the universe is a realm of constant transformation, where the past is preserved in the present and the future is shaped by the echoes of what came before. As we look to the skies and ponder the significance of these celestial wanderers, we are reminded of the vastness of existence and the enduring wonder that drives our exploration of the unknown. In the vast dark expanse of the universe, comets have always been enigmatic travelers. They streak across the night sky like whispers from the void, carrying secrets of the cosmos' earliest moments. For millennia, humanity has gazed upward, interpreting these glowing wanderers as omens, myths, or divine messages. Yet in the age of science, comets have become something far more profound: celestial laboratories, cosmic messengers, and portals to understanding our place in the universe. The year 2025 brought 3 such comets into our field of view: C2025 F2 SWAN, 3I Atlas, and C2025 R2 SWAN, each a thread in the intricate tapestry of the cosmos. Their stories are not merely tales of icy nuclei and dusty tales, but reflections of the universe's boundless creativity, its cycles of birth and decay, and the delicate dance of forces that govern existence. C2025 F2, a fragile comet from the distant reaches of the solar system, offered a fleeting glimpse of beauty before disintegrating under the sun's relentless pull. 3I Atlas, an interstellar wanderer born in the depths of another star system, arrived as a silent envoy of the galaxy's hidden history. And C2025 R2, a recent apparition, hinted at the possibility of a meteor shower, a brief but vivid connection between Earth and the cosmos. Together, these comets invite us to ponder the impermanence of celestial phenomena, the infinite scale of time, and the interconnectedness of all things. They remind us that the universe is not static but alive, a dynamic entity where every event, no matter how small, ripples outward in ways we are only beginning to comprehend. C2025 F2, SWAN, was first detected by the Solar and Heliospheric Observatory's MAOHO SWAN instrument in late March 2025. Its presence revealed in images captured by the Solar Wind Anisotropies camera, discovered by astronomers Vladimir Bezugli, Michael Matiasso, and Rob Matson. The comet was initially a faint smudge of light against the backdrop of space, its magnitude around 11. Over the following weeks, it brightened, offering hope that it might become a spectacle visible to the naked eye. However, its fate was sealed by the fragility of its nucleus. By mid-April 2025, C2025 F2 had reached a peak magnitude of 9.2, its coma expanding into a luminous sphere 2 arc-minutes wide. Ampere's dramatic outburst on April 5th briefly elevated its brightness to 8.6, but this surge signaled the comet's impending demise. The intense solar radiation and gravitational tides tore apart its nucleus, scattering dust and gas into a diffuse cloud. By April 22nd, the core had vanished entirely, leaving only a ghostly trail of debris. This disintegration, captured by observatories worldwide, underscored the precarious existence of comets, which often originate from the distant Kuiper belt or Oort cloud. These icy bodies, formed over 4.6 billion years ago, are relics of the solar system's infancy, yet their journeys into the inner solar system are fraught with peril. C2025 F2's orbit, calculated using precovery images dating back to September 2024, revealed a nearly parabolic trajectory, with an estimated orbital period of 80,000 years. It had spent the last 40,000 years hurtling inward from a distance of 3,750 astronomical units, AU, a journey spanning 561 billion kilometers. Its perihelion, at 0.333 AU, 49.8 million kilometers, placed it just inside Mercury's orbit, where temperatures soared to levels capable of sublimating its volatile ices. The comet's final months were a testament to the universe's duality. The same forces that birthed stars and planets could also unravel them in moments of cosmic violence. While C2025 F2 was a product of our solar system, 3I Atlas arrived from beyond. Discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS, on July 1, 2025, this interstellar comet was the third such object ever identified, following 1I Oumuamua and 2I Borisov. Its hyperbolic trajectory, defined by an orbital eccentricity of 6.14, betrayed its extraterrestrial origin, traveling at a velocity of 58 kilometers per second. Relative to the Sun, far exceeding the escape speed of the solar system. 3I Atlas was destined to vanish into the void after its brief visit. Spectroscopic analyses revealed a nucleus rich in carbon dioxide, water ice, and organic compounds, suggesting it formed in a cold, distant environment. Observations by the James Webb Space Telescope, JWST, and the Hubble Space Telescope uncovered traces of cyanide and nickel vapor, elements commonly associated with cometary activity in our own solar system. Yet 3I Atlas's chemical composition hinted at a different history. Its origin, traced to the direction of the Milky Way's galactic center, pointed to an age potentially exceeding 7 billion years longer than the 4.6 billion-year-old solar system itself. The comet's path brought it to perihelion on October 29, 2025, at a distance of 1.36 AU 23 million kilometers, placing it between Earth and Mars. Despite its proximity, 3I Atlas remained a faint object, never surpassing magnitude 11.5 from Earth. However, its passage offered a rare opportunity to study an alien world. The data collected by observatories like the Very Large Telescope and the Vera C. Rubin Observatory provided insights into the diversity of planetary systems and the mechanisms that launch objects into interstellar space. 3I Atlas was not just a visitor, it was a message from the unknown, a reminder that the universe is teeming with mysteries waiting to be unraveled. C 2025 R2, SWAN, discovered by Vladimir Bezugli on September 11, 2025, emerged as a striking anomaly. Unlike its predecessors, this comet was poised to interact directly with Earth. Its orbit, determined through observations by SOHO's SWAN instrument, intersected Earth's path in October 2025, raising the possibility of a meteor shower. The comet's rapid brightening, from magnitude 11 to 6.2 in just a month, suggested a volatile nucleus, likely composed of fragile ices and dust. C 2025 R2's perihelion occurred on September 12, 2025, at a distance of 0.5 AU 75 million kilometers. A relatively safe encounter with the Sun. However, its closest approach to Earth, 0.26 AU 39 million kilometers, on October 19, 2025, meant that its debris trail could collide with our atmosphere. Meteor showers, born from the remnants of comets, are fleeting but profound reminders of the universe's interconnectedness. If C 2025 R2 produced a display, it would be a tangible link between Earth and the cosmos, a shared moment in the grand narrative of cosmic evolution. The comet's orbit, still poorly understood due to its recent discovery, hinted at a long-period trajectory. Estimates varied widely, from 1,400 to 20,000 years, underscoring the challenges of predicting the paths of celestial bodies. This uncertainty mirrored the human condition, our attempts to map the universe, to find patterns in chaos, to grasp the infinite within the finite. C 2025 R2, like all comets, was a transient phenomenon, a reminder that even in permanence, nothing is eternal. Comets are more than frozen wanderers. They are cosmic archives, preserving the conditions of their birthplaces. C 2025 F2, 3I Atlas, and C 2025 R2 each reflect different chapters in the universe's story. C 2025 F2's disintegration highlighted the vulnerability of solar system objects, their fates dictated by the Sun's gravitational and thermal forces. 3I Atlas, in contrast, embodied the universe's vastness, a relic from a distant star system that had traveled millions of years to reach us. C 2025 R2 bridged these extremes, a local comet whose potential meteor shower could offer a visceral connection to the cosmos. The study of these comets deepens our understanding of the solar system's formation. C 2025 F2's origin in the Oort cloud, a hypothetical spherical shell of icy bodies at the solar system's edge, supports the theory that comets are primordial remnants of the protoplanetary disk. 3I Atlas, meanwhile, challenged our assumptions about the frequency of interstellar objects. Its high orbital inclination and retrograde motion suggested it originated from the Milky Way's thick disk, a population of older stars with distinct chemical compositions. Such findings imply that interstellar comets are not rare anomalies, but part of a larger unseen flux of material exchanged between stellar systems. Comets play a pivotal role in shaping planetary systems. Their collisions with planets, like the hypothesized impact that delivered water to Earth, illustrate the dynamic processes that forge habitable worlds. 3I Atlas's carbon dioxide-rich composition, for instance, offers clues about the chemistry of distant star systems. If such comets frequently migrate into other planetary systems, they could seed life's building blocks across the galaxy. The potential meteor shower from C2025 R2 underscores the cyclical nature of cosmic interactions. Meteor showers, though fleeting, are the universe's way of recycling. The dust and gas released by dying comets become raw materials for new stars and planets, perpetuating the cycle of creation and destruction. This process, occurring on scales both immense and infinitesimal, is a testament to the universe's resilience and ingenuity. The 2025 comets also reflect humanity's evolving relationship with the cosmos. From ancient stargazers to modern astrophysicists, we have sought to decode the heavens. The discovery of 3I Atlas in particular marked a milestone. For the first time, we could observe an object that had originated in another star system. This achievement was not just technological but philosophical, a recognition of our smallness within a vast interconnected web of existence. Yet the comet's fates, C2025 F2's disintegration, 3I Atlas's departure, and C2025 R2's potential shower, also mirror our own. Like these celestial bodies, we are transient, our lives brief in the cosmic timeline, yet in that brevity lies meaning. Every observation, every data point, is a step toward understanding the universe's grand design, a fleeting but vital contribution to the collective human endeavor. As the 2025 comets faded from view, their legacies endured in data, in stories, and in the questions they inspired. What other interstellar visitors await discovery? How do comets shape the destinies of planets, and in turn life itself? The answers lie not just in the stars, but in our relentless curiosity, our drive to explore the unknown. The universe is a symphony of motion and stillness, of birth and death, of order and chaos. Comets are its notes, played across the infinite. To study them is to listen closely, to hear the echoes of the past and the whispers of the future. And as we look to the next chapter of cosmic exploration, we carry with us the lessons of 2025, the reminder that even in the void, there is purpose. Even in the fleeting, there is eternity. In the vast, silent expanse of the universe, comets drift like ancient mariners, their icy nuclei glowing faintly as they trace paths etched by the gravitational hands of stars. These frozen relics, born in the frigid outskirts of planetary systems, are more than mere visitors. They are cosmic archives, carrying secrets of stellar nurseries, the birth of planets, and the raw ingredients of life itself. Among the countless comets that have ever been observed, 3 stand out in the annals of 2025. C2025 F2, SWAN, the disintegrating spectre of the inner solar system; 3I Atlas, an interstellar wanderer from the depths of the Milky Way; and C2025 R2, SWAN, a fleeting beacon poised to brush against Earth. Together, they illuminate the profound interconnectedness of the cosmos, reminding us that even the smallest specks of ice and dust can reshape worlds. Comets are the universe's storytellers. Their tails, formed as solar radiation sublimates volatile ices, scatter light like whispers of forgotten epochs. When we gaze at a comet, we are not merely seeing an object. We are witnessing a collision of forces, the pull of gravity, the push of sunlight, and the chemistry of distant stars. The stories they carry are written in gases, in the scars of their surfaces, and in the dust they leave in their wake. To understand comets is to grasp the heartbeat of the cosmos, a rhythm that spans billions of years and transcends the boundaries of individual solar systems. This script delves into the lives of these 3 comets, each a chapter in the epic saga of cosmic evolution. From the disintegration of C2025 F2 to the interstellar odyssey of 3I Atlas and the potential meteor shower of C2025 R2, we embark on a journey through time and space. Along the way, we uncover how comets are not passive spectators, but active participants in the drama of planetary formation, climate change, and the emergence of life. Let us begin by unraveling the tales of these celestial travelers. Their journeys as much a mirror of our own quest for knowledge as they are a testament to the universe's boundless creativity. Discovered in late March 2025 by Vladimir Bezugli, Michael Matiazo, and Rob Matson, through images captured by the Solar and Heliospheric Observatory's SWAN instrument. C-2025-F2, SWAN, was destined to be a spectacle. Initially detected at a magnitude of 11, its brightness surged as it neared the Sun, offering astronomers hope that it might reach magnitude 5 by May. Yet as the comet approached perihelion, its fate took a tragic turn. By mid-April, observations revealed a sudden fading, followed by complete disintegration. By 22 April, its nucleus had vanished, leaving behind only a ghostly dust cloud. The comet's journey was brief but instructive. Originating from the Oort cloud, a vast reservoir of icy bodies at the edge of the solar system, C-2025-F2 followed a nearly parabolic orbit, spending 40,000 years inbound before succumbing to the Sun's heat. Its disintegration highlights the fragility of comets, whose volatile compositions make them vulnerable to solar radiation. Yet even in its demise, C-2025-F2 contributed to the cosmic tapestry. The dust it released will linger in the inner solar system, a temporary gift to the zodiacal cloud, a diffuse band of interplanetary dust that glows faintly in the twilight. While C-2025-F2 was a local traveler, 3I Atlas hailed from the far reaches of the galaxy. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile, this interstellar comet entered the solar system at a blistering speed of 58 kilometers per second. Unlike the two previous interstellar visitors, 1I Oumuamua and 2I Borisov, 3I Atlas followed an extraordinarily hyperbolic trajectory, with an orbital eccentricity of 6.141, making its path appear almost straight rather than curved. What sets 3I Atlas apart is its chemistry. Spectroscopic analysis by the James Webb Space Telescope revealed an unusual richness in carbon dioxide, alongside traces of water ice, carbon monoxide and cyanide. These compounds, common in our own solar system's comets, suggest that 3I Atlas's parent star system may share similarities with our own. Moreover, its age, estimated at 7 to 14 billion years, places it among the oldest objects in the Milky Way, predating the formation of the solar system. As 3I Atlas hurtles toward perihelion, on 29 October 2025, it will pass within 0.19 AU of Mars, offering an unprecedented opportunity for robotic missions to study an interstellar object up close. Yet despite its scientific value, 3I Atlas remains a faint whisper in the night sky, peaking at magnitude 11.5, visible only through telescopes. Its transient presence serves as a reminder of the galaxy's vastness and the ceaseless exchange of material between stars. The youngest of the trio, C-2025-R2, SWAN, was discovered on 11 September 2025 by Vladimir Bezugli, using SOHO's SWAN instrument. Unlike its predecessors, C-2025-R2 is a resident of the solar system, though its origins remain shrouded in mystery. With an orbital period estimated at 1,400 to 20,000 years, the comet will reach perihelion at 0.5 AU on 12 September 2025, followed by a close approach to Earth on 19 October 2025. What makes C-2025-R2 remarkable is its potential to create a meteor shower. As Earth crosses its orbital path on 5 October 2025, particles ejected from the comet's nucleus may enter the atmosphere, producing a celestial display. Though the intensity remains uncertain, the event offers a rare chance to study the interaction between cometary debris and planetary environments. Comets are often called dirty snowballs, but their true nature is far more complex. Beneath their icy exteriors lie molecular treasures, amino acids, water, and organic compounds essential for life. 3I Atlas's detection of cyanide and carbon dioxide echoes the chemistry of primordial Earth, where such substances may have seeded the first biochemical reactions. Similarly, the dust of C-2025-R2 could contain silicates and carbon-rich grains, materials that, when delivered to young planets, might catalyze geological and atmospheric changes. The idea that comets deliver water and organic molecules to planets is not mere speculation. Studies of carbonaceous chondrites, meteorites believed to originate from comet-like bodies, show that they contain hydrated minerals and complex organic compounds. If 3I Atlas's composition mirrors that of exoplanets, it could guide the search for habitable worlds. By analyzing its gases and isotopic ratios, scientists might infer the conditions under which it formed, shedding light on the diversity of planetary systems beyond our own. Comets are not passive messengers. They are active forces in shaping planetary evolution. The meteor shower generated by C2025R2 could provide insights into how cometary impacts influence climate and geology. On early Earth, such events may have delivered water to arid landscapes, while on Mars, they might have contributed to the formation of transient lakes and rivers. Even today, the zodiacal dust left by disintegrating comets, like C2025F2, plays a role in the solar system's energy balance, scattering sunlight and influencing temperature gradients. The interstellar nature of 3I Atlas adds another layer to this narrative. Its arrival underscores the dynamic exchange of material between stars. In the Milky Way's crowded core, where gravitational interactions are frequent, comets might be flung into interstellar space as easily as they are captured. Such processes suggest that the building blocks of life are not unique to our solar system, but are shared across the galaxy, a cosmic inheritance that blurs the lines between local and alien. Yet comets are also reminders of impermanence. C2025F2's disintegration and 3I Atlas's rapid escape from the solar system highlight the fragility of existence. For comets, survival is a balancing act between the sun's destructive heat and the gravitational tethers of planets. Similarly, life on Earth is vulnerable to cosmic impacts and environmental shifts. By studying comets, we confront the duality of creation and destruction. The same forces that give rise to planets and life can also erase them. This duality is particularly evident in the case of C2025R2. While its meteor shower may inspire awe, it also serves as a cautionary tale. The same particles that dance in Earth's atmosphere could, in a different context, devastate ecosystems. Understanding cometary behavior is not just an academic pursuit. It is a matter of planetary survival. As technology advances, our ability to study comets grows exponentially. Instruments like the James Webb Space Telescope, the Vera C. Rubin Observatory, and the European Space Agency's Comet Interceptor mission promise to revolutionize our understanding. These tools will allow us to peer into the hearts of comets, mapping their compositions in unprecedented detail, and tracing their origins to the earliest epochs of the galaxy. Yet, for all our progress, comets remain enigmatic. Each discovery raises new questions. What other interstellar travelers lurk in the darkness? How do cometary collisions shape the destinies of planets? What secrets lie in the dust of a dying comet like C2025F2? As we prepare for the next great comet, we must remember that every icy visitor is a thread in the fabric of the cosmos, a reminder that we are part of a story far older and vaster than ourselves. In the coming decades, humanity's gaze will extend beyond the solar system, seeking comets in distant star systems and decoding their messages. The legacy of C2025F2 3I Atlas and C2025R2 will endure as milestones in this journey, a testament to the power of curiosity and the infinite wonders of the universe. The universe is a vast, silent expanse where time stretches into epochs unfathomable to the human mind. Yet within this boundless darkness, transient wonders emerge: comets, those ancient wanderers born of ice and dust, streaking across the heavens like ephemeral brushstrokes on the canvas of eternity. In 2025, 3 such comets captured the attention of astronomers and stargazers alike: C2025F2 SWAN, 3I Atlas, and C2025R2 SWAN. Each told a story of cosmic origins, perilous journeys, and fleeting brilliance. Together, they illuminated the fragility and grandeur of existence, reminding us that we are but a single thread in a tapestry woven over billions of years. C2025F2 SWAN began its tale in the cold depths of the outer solar system, a relic from the birth of the planets. Discovered by the Solar and Heliospheric Observatory's MALHO SWAN instrument in late March 2025, it was expected to shine brightly in May, a beacon for backyard observers. Yet as the comet approached the sun, its story took a tragic turn. Its nucleus, weakened by millennia of solitude, fractured under the solar inferno, scattering its essence into a ghostly shroud of dust. Meanwhile, 3I Atlas, the third interstellar visitor ever recorded, swept into the inner solar system from the far reaches of the Milky Way. With a hyperbolic trajectory and a speed unmatched by any native comet, it hinted at origins older than Earth itself, carrying secrets of alien star systems. And then there was C2025 R2, SWAN, a sudden apparition that flared unexpectedly in September 2025, its tail stretching like a celestial arrow across the sky. These comets, each distinct yet united by their cosmic paths, invite us to ponder our place in a universe teeming with mysteries. Comets are more than frozen wanderers, they are time capsules, preserving the primordial material of the solar system. Their nuclei, composed of ice, rock and organic compounds, are remnants from the solar nebula that coalesced into planets some 4.6 billion years ago. When these icy bodies venture too close to the sun, they awaken. Solar radiation sublimates their surfaces, releasing jets of gas and dust that form the glowing coma and sweeping tails we see. This process, both destructive and transformative, reveals their hidden chemistry. For example, 3I Atlas, with its unusual abundance of carbon dioxide and cyanide, offers a glimpse into the volatile chemistry of interstellar space. Such discoveries challenge our understanding of planetary formation, suggesting that the building blocks of life may be more widespread in the cosmos than previously imagined. The discovery of comets like C2025 F2 SWAN and C2025 R2 SWAN underscores the power of modern technology. Soho's SWAN camera, designed to map the solar wind in Lyman R light, inadvertently became a comet hunter, spotting these objects against the backdrop of the Milky Way. These instruments, coupled with ground-based telescopes and the ingenuity of amateur astronomers, allow us to track comets with unprecedented precision. Yet, even with advanced tools, predicting a comet's fate remains a delicate art. C2025 F2's disintegration in April 2025, for instance, was a sobering reminder of the fragility of these celestial bodies. Its nucleus, subjected to intense solar heating, fragmented into a diffuse cloud of debris, fading from view before it could fulfill its promise of a brilliant display. Such events are not uncommon in the realm of comets, where survival is a gamble against the forces of entropy. Interstellar comets like 3I Atlas complicate this narrative. Unlike their solar system-born counterparts, these travelers originate from other stars, their trajectories shaped by the gravitational tides of distant galaxies. 3I Atlas's hyperbolic orbit, a path so elongated that it escapes the sun's gravitational pull, proves its extraterrestrial origin. Its arrival in 2025, at a velocity of 58 kilometers per second, marked it as the fastest moving interstellar object yet observed. This speed, combined with its trajectory tilted 5 from the ecliptic, suggests it hails from the thick disk of the Milky Way, a region populated by ancient stars. If this hypothesis holds, 3I Atlas may be over 7 billion years old, predating the solar system by eons. Such a finding would rewrite our understanding of the timeline of cosmic evolution, revealing that interstellar comets have been traversing the galaxy long before humans gazed up at the stars. The study of these comets also highlights the role of spectroscopy in unraveling their secrets. Instruments like the James Webb Space Telescope, JWST, and the Hubble Space Telescope have dissected the composition of 3I Atlas's coma, identifying molecules such as water vapor, carbon monoxide, and nickel. These signatures hint at the comet's history. Perhaps it formed in a cold, dark molecular cloud, where volatile ices condensed, or it was ejected from a planetary system by gravitational chaos. Similarly, the detection of cyanide in 3I Atlas's tail echoes the chemistry of comets in our own solar system, bridging the gap between the familiar and the alien. Such findings fuel speculation about the universality of prebiotic chemistry. Could interstellar comets have seeded life on Earth, or do they carry the building blocks of life elsewhere in the cosmos? The 2025 comet season was a testament to the democratization of astronomy. While professional observatories like the Vera C. Rubin Observatory and the James Webb Space Telescope pushed the boundaries of scientific inquiry, amateur astronomers played an equally vital role. Vladimir Bezugli, Michael Matiasso, and Rob Matson's discoveries of C2025 F2 SWAN via SOHO imagery exemplified the synergy between grassroots efforts and cutting-edge technology. Similarly, the early detection of 3I Atlas by the Atlas Survey in Chile showcased how automated sky scanning systems can uncover rare phenomena. This collaborative spirit reflects a broader shift in science, the recognition that curiosity is not confined to laboratories or institutions, but thrives in every corner of the globe. Yet the implications of these discoveries extend beyond academia. The disintegration of C-2025 F2 SWAN raised questions about the resilience of celestial objects and the forces that govern their fates. Why did this comet, once poised to become a binocular marvel, succumb to the sun's wrath? Was its nucleus inherently fragile, or did its orbital path subject it to conditions it could not withstand? These questions mirror humanity's own struggle against entropy, a universal law that dictates the decay of all things. Comets, in their brief moments of glory, remind us that beauty and transience are intertwined. Meanwhile, 3I Atlas posed a more existential query. What does it mean to encounter an object from another star system? The comet's interstellar origin, confirmed by its hyperbolic trajectory, forced astronomers to confront the reality that our solar system is not an isolated haven, but a node in a vast network of celestial highways. The fact that 3I Atlas passed within 0.19 AU of Mars in October 2025, yet posed no threat to Earth, underscored the statistical rarity of such encounters. Still, the possibility of future interstellar visitors looms large. If 3I Atlas is representative of its kind, the Milky Way may be teeming with rogue comets and asteroids, each carrying stories of their home systems. Could these interstellar travelers harbor alien life, or at least the precursors to life? Such questions blur the line between science and philosophy, inviting us to reimagine our place in the cosmos. The fleeting brilliance of C-2025 R2, SWAN, added another layer to this narrative. Discovered just days before its perihelion, the comet's rapid brightening defied predictions, a reminder of the unpredictability inherent in astronomical phenomena. Its potential to create a meteor shower when Earth crosses its orbit in October 2025 offered a tangible connection between comets and human experience. Meteor showers, often described as tears from comets, are reminders that we live in a dynamic universe, one where the remnants of ancient ice rain down on us like whispers from the past. As the year 2025 drew to a close, the legacy of these comets lingered in the minds of those who witnessed their journeys. C-2025 F2 SWAN taught us humility, its demise a stark reminder that even the brightest stars fade. 3I Atlas expanded our horizons, its interstellar origins a bridge to the unknown. And C-2025 R2 SWAN reminded us of the universe's capacity for surprise, a spark of mystery in a world increasingly defined by data. Together, these comets wove a narrative of impermanence and wonder, urging us to look beyond the immediate and embrace the infinite. Yet the story is far from over. Future observatories, such as the Vera Rubin Observatory, promise to uncover more comets, both native and interstellar, before they vanish into the void. Missions like the European Space Agency's Comet Interceptor aim to intercept such travelers, offering unprecedented opportunities to study their surfaces up close. As these technologies mature, the line between observation and exploration will blur, opening new chapters in humanity's cosmic saga. Perhaps one day, we will follow a comet like 3I Atlas back to its stellar birthplace, tracing the threads of the universe's tapestry to their source. Until then, we remain stargazers, forever drawn to the dance of light and shadow across the heavens, seeking meaning in the silence of the stars.